Good afternoon, dear students. Can you hear me?
Yes, I can, teacher.
Yes,
Okay, thank you. Thank you for feedback. So let's continue from our last lesson. I'm going to share the screen with you and we'll continue with PowerPoint presentation. Okay. So last week we started to talk about synthesis, design the mechanism. That means if we go back to the beginning of the lessons, we said the previous chapter explored methods to determine the displacement of a mechanism whose link lengths are given. So we did it in previous chapter. So now, compared to these analyses, the design of a mechanism presents the opposite task, that is, given a desired motion, a mechanism form and dimensions must be determined. That means synthesis. So this is what we call synthesis of the mechanism. And we talked about, we said we will mainly deal two types of mechanism, slider crank mechanism and the four-bar mechanism, because they are the often used mechanisms in the machinery. and we already started with slider crank mechanism, inline and offline. You know, we all discussed in our previous lessons. So then finally we came to the online, offline, all of them we discussed, and finally we came to the topics of four-bar mechanism. So slider crank mechanism, online, inline or offline, we discussed already. And also you can check you can write a simple program and you can check the displacement of the point C here. I mean the slider, displacement of the slider with the angle of the crank. So I call the transfer function, like we discussed in the previous chapters. So transfer function. That means I drive the crank, the L2, in clockwise or counterclockwise, and I calculate the position of the C and see how does it how this the position of the C is changing with respect to driving angle or driver angle. I have an example for you, and you have to do also on your own. Inline slider crank mechanism, for example, I use the Excel, but you can use MATLAB or another program. You see here what is given. L1 is given. Where is the L1? So here, this is the L1 you see here. L1 is given. L1, L2, and L3 has to be given, because at the end of the analysis we can we can find out or calculate all these dimensions for a given or desired motion. Then we have to check it, is it okay or not? And I check, for example, the motion of the point point C here with respect to the driving angle, and you see the L1 is 0, and we can also give another value. If L1 is 0, then that means it is inline slider crank mechanism, and L2, L3, and then theta 2 is the driving angle, and theta 3 we have to calculate, and gamma we have to calculate, and L4 is we have to calculate. This is the L4 here. You see here the distance in between here. So, and then you see the function here. A stroke changing with the driving angles, and this is very very interesting curve actually. You know, if the driving angle is 0 and displacement is also 0, it starts from the limiting position, and then go forward and arrive its final position. That means the maximum stroke. This is the maximum stroke, and you know here is about 100, I don't know, 2 or 3, 5, and we can see that here to check it. Maximum stroke is L2 plus L3, and this is here L2 plus L2 plus L2 plus L3, and this is 254, and this is so 100. No, it is something here is actually given here. Okay. So it is, so it is not 100, so the stroke is, sorry, I'm miscalculating. Stroke is actually, and let's calculate it. Stroke is like, you know, L2 is 2 times L2, and 2 times L2 is L2 is 100, correct, is 51 times 2 is 100, 102 is the maximum stroke, and you see here it starts from 0 and 100, 102 around maximum stroke, and then come back. So it needs 180 degrees here, somewhere 180 degrees. We can oh, is that here? I can't find. Okay, so this is here somewhere, so it must be in the middle actually. And let's use the correct one, and so you see it is somehow here, and in the middle, huh? So this is 100, the maximum stroke is 102 around, and the 180 degrees in the middle. So this is inline mechanism, like this one. Where is it? Here, like this one is the inline mechanism. So the inline mechanism, and the stroke is defined by the length of L2, and 2 times L2. This is the one of the let's say the minimum stroke. If it is in this position, if it is in this position, maximum stroke. So that means the length of stroke is 2 times of L2. We actually learned in the design, and you can check also here, writing a simple program. You can check it. So over the driving angle, you see how the point C is changing its position, and this is the path or curve. The point C undergoes. It's very important, very interesting. So the first derivation of this curve, you will learn that, and first derivation of this curve, derivation with time, will give us the velocity, and we can calculate that analytically. First derivation is the velocity. That means we can calculate the velocity as a curve, as a part of this point C, and we can also calculate the acceleration later on. The next chapter will be velocity, and then we will talk after the next chapter about the acceleration. So that means we are able to calculate the velocity and acceleration of any points on the mechanism. So, okay, so let's continue then with the new topics. That means new topics for bar mechanism. So the 4-bar mechanism are also used in the machinery. In slider crank mechanism, our interest was actually said that the stroke was given. Stroke, you see here the stroke delta L. So this is the delta R is given, and for a given delta R, that means mainly in industry. So you see, we convert the rotary motion into the linear motion, and into linear motion, rotary motion, we can, let's say, create using electric motor, we can get it. But the translation, linear motion, for that we need a mechanism. So to convert the rotary motion into the linear motion. And then the important is for the designer to know the length of the stroke. So we have to design a mechanism for a given stroke length. That was the question in the first part of this chapter. And the second part of this chapter is the, so the 4-bar mechanism, the angle here, the angle. This is our, let's say, the required or desired quantity, or we have to design a mechanism in order to achieve for a given angle here between blue and the red. Huh? So this is the given of rocker. Say this is the angle of rocker creates for a full rotation of the crank. That means L2. So in general, a 4-bar mechanism has quick return actions. Quick return actions we also discussed in slider crank mechanism. And we said quick return sometimes important because the forwards motion of a of a moving part is mainly used for a process, and process maybe has a special speed, so we cannot drive too fast. So therefore, the speed for the advanced stroke or advanced motion has to be controlled and adjusted according to the needs of the process. But in case for the return, many applications for the return, there is no limitation, or there is no, let's say, any expectation, because the expectation is in terms that it should become as soon as possible back to start a new cycle. So that means it affects the cycle time, and therefore, as soon as possible, after achieving the advanced stroke, the mechanism should come to the initial position to start the next cycle. So quick return, that means quick return actions. So to reduce the cycle time. And it must determine the required Q and beta. So what is beta? So Q, the ratio. Q was the ratio we already discussed in previous lesson. And beta is the imbalance angle. So beta is imbalance angle. So the task is to determine appropriate L1, L2, and L3, and L4. That means all length of all the links. So to achieve the required delta 4 maximum and the beta. So that means, so what is given? Actually, we can say given. So what is given? Let's write here given is actually delta theta 4 we expect. So delta theta 4, this one here, maximum, let's say, the max length, max angle, max, and for the quick return, beta is given. So then we have to. So if we have to, if there is, if the angle is required, so then that means we need a 4-bar mechanism, general 4-bar mechanism like this. So if the stroke is required, so we need a crank slider mechanism. It's very clear, huh? to select the type of the mechanism. So then, in case angle here, so then angle should be given, must be given, and the beta also for the quick return, and then we have to calculate the L1, L2, L3, and L4 for a desired delta theta 4 max and beta. So how can we do that? So let's continue with the 4-bar mechanism. And let's say, let's have a general picture of 4-bar mechanism and display all the relations regarding the dimensions and the angles. That means the geometric dimensions or geometric parameters, so that we know what is given and what is required, and how can we solve it. And you see here, we need, we learned in the previous chapter, the limiting positions. So there are 2 limiting positions. Actually, this blue one is the one of the limiting position, and the red one is the others of the limiting position. And you see, in limiting position, it seems like the red one, so the limiting position here, and in that position, L3 and L2 is the total length here. L2 and L3, L2 plus L3. L4, okay. This is the initial arbitrary set. We can use any let's say the arbitrary position. We can start from any arbitrary position. But important is the length, the angle here to realize. And if we start from here, you can see that. Let's say we start from here and we select this angle arbitrarily. I mean this angle here. For this position, we select arbitrarily. And then the angle theta 4, and then this is the initial position, which this is the one of the limiting position, the red one, where L2 and L3 are in line. So the other one, I mean the second position to realize the delta theta 4 max is the blue one. And for the blue one, you see also L2 and L3 in line, but we have the the length is here L3 minus L2, because here's the L2 here, this is here L2 L2, and the total length is here. Total length is L3 L3, so, and the length here in between is L3 minus L2. Okay, so often L1 has a target value. L1, where is the L1? This one. So you have to consider also where you are going to apply the mechanism and how much space you have in the machine. And L1 is actually mainly, let's say, the given let's say checking the conditions in the machine where we want to apply the mechanism. So L1 has a target value. That means in order to install into the machine, so we have to let's say select the L1. So after construction, all other dimensions can be scaled to achieve the desired L1. So then, after finishing all the design, so then you have to check again L1 is correct or not, or shall we change, because there are many solutions regarding the dimensions, not only one or two. So the transmission angle gamma is here. So the angle between coupler and the follower link, that means here, let's show it in that way. So this is the angle here, gamma. So angle between coupler and the follower link, and the coupler is a two-force member. Okay, the coupler is two-force member, we know from the static. And rule of thumb is the gamma must be between 40 and 140. So this is important, 40 and 140. Why? Because of the power transmission. So if it's smaller or bigger, then the power transmission, it affects power transmission, and the efficiency of the power transmissions will be affected in a negative way. So the optimum, let's say the power for optimum power transmission or the motion transmission, the rule is gamma in between 40 and 140. Okay, so then design of a crank rocker mechanism. Let's design. So how can we design it? Crank rocker mechanism. You see here we have an example A, B. So here we have A, B, and C here, and D. So how can we realize the design step by step? First, a crank rocker mechanism has also been discussed on several occasions before we discussed. It is common for many applications where repeated oscillations. So this is the oscillation, you know, here in between. I can show you now here. This is the type of oscillation here. Huh? So here in between, this is the, and this is the oscillation angle. And this is actually the main required quantity or required properties. Oscillation. So this is the oscillation, repeated oscillations. So this is R required quantity. So on this figure A here illustrates the geometry of a crank rocker comparable to the stroke of a slider crank mechanism. The crank rocker mechanism exhibits a true angle, that means delta theta 4 max, figure A. This true angle is defined as the angle between the extreme positions of the rocker link. So this is the extreme position, that means limiting position. Huh? These two positions are limiting position. Let's cover it. So this is the C1 here, and this is the C1 here, you see, and it's the C2 position here. So in between, the rocker is oscillating. Okay. This true angle is defined as the angle between the extreme position of the rocker link. Okay. So the design of a crank rocker mechanism. The design of a crank rocker mechanism involves determining appropriate lengths of all 4 bar links to achieve the desired true angle, delta theta 4 max, and imbalance angle beta. So the graphical procedure to synthesize, that means to create a crank rocker mechanism is as follows. So you see step by step. So first, what we should do? First, locate the pivot of the rocker link point D in figure B. So we select the point D somewhere. This is the point the rocker turning around or about. Then choose any feasible rocker length L4. We can select any feasible length L4. This length is typically constrained by the special allowance for the mechanism. So to select free, okay, you can say we can select free, but we have to consider always where we are going to use these mechanisms, to apply these mechanisms, and how much space we have. So there are also some constraints from this side, the machine side, and this length is typically, or affected from the place given by the machines. So there are the two positions of the rocker. So let's say we select the length here. Okay, let's use that here. And we select these two length, the length of 4, and there are the position L, C1 and C2. C1 and C2, because this angle is also given. Huh? Well, there are the two positions of the rocker. Okay, we did it. Separate the throw angles. We showed the throw angles also okay here. So, and for at one of the extreme position, construct any line M. So this is the line M here. Let's use another color, a line M. So this is the line M here. Any line M. We design, and how can we draw it? The angle theta M is important here. We selected theta angle, huh? And this theta angle, that means theta angle with respect to horizontal line. So, and this is our line M. Okay. So then, in line M, okay, through the end of the rocker link and inclined at any angle theta M. Okay. This point is labeled C2 in figure B. Okay, you see here, this is the C2, huh? C2. Okay. At the other extreme position, now we come to the other extreme position. Let's use another color. This one maybe. This here, we have draw also a line like this with delta theta, theta n. But the important is we have to realize the beta here. So beta we have to realize it. Beta is very important. So two line, you know, we are drawing two line from two extreme positions or limiting position of rocker using selecting the theta n and theta m. But at the end, if we have this triangle like this here, so this angle must be beta, so given, which is given. So then we have also this relation here. That means if we consider this triangle, actually we select only theta m. So theta m, we select the length 4, and then we use the delta theta 4, and we create the position, the other position C1 and C2 to extreme position or limiting position. Then we selected theta m and draw the line M, and you see theta n has to be calculated with respect to theta m and beta. Beta must be given. The imbalance angle. So then we intersection of these two lines here, the point A is the crank pivot A. So crank, let's move to the other picture. So that means this is the here the point A. So the intersection of lines M and N defines the pivot point for the crank points A. The length between the two pivots L1 can be scaled from the constructions figure C, like here, and then for case where balanced timing is required, Q1, lines M1 and N are collinear. So this pivot point for the crank point A can be selected anywhere along line M and N. So here, from here, we know that you can imagine here. So this we have this point. If we have the A, you see here, we already defined the A, and since we have the A, and in this position, sorry, you can say in this position. So this position, this is L2 and L3, and this position, this is L here. The maximum length is the L2 we can get from the drawing L2, and L3 also we can calculate. So then we have all, I mean L2, L3, and L4 we had selected at the beginning. So then actually we create the mechanism. So, and then we can optimize it by selecting a certain scale. You know, with a certain scale, you can reduce or increase the length of the links, but with a certain scale must be proportional. So then you see here also some equations here given, but this is the way how can the design crank rocker mechanism for a given imbalance angle and the oscillating angle here like this. Okay. An additional measurement, and here an additional measure of the quality of a 4-bar mechanism is the transmission angle, and this is the here transmission angle, huh? In limiting positions. That means we have two limiting positions, and it must be between, we discussed already at the beginning, it must be between 40 and 140, and it shouldn't be exceed 40 and 140. This is the so this is the angle between the coupler and the rocker, as illustrated here figure. I've shown that. So a common functions of a 4-bar link is to transform rotary into the oscillation. This is interesting. So to transfer functions of the convergence length is to transfer rotary motion into the oscillating motion. So if there's such a task or problem, then we can use the crank rocker mechanism. Frequently in such applications, a large force must be transmitted. So the force or power has to be also transmitted via these links. Also large Also, large force must be transmitted. And in this situation, to transfer to the force, in these situations, the transmission angle gamma becomes of extreme importance. You know, this is a two force member, and you can easily imagine if there is such a force here, not the topic for here for today's, but I will mention it. So here, let's say this is the force, our force here, coming from the driver, and this is the direction here. And this is the force. And the important portion of this force is actually the perpendicular part. This is perpendicular to this rocker, because this is the driving force. And this part, this portion or this component, that means the vertical components of this force, is going through the fixed point here, the bearing. So if we have a small angle, as small as possible, then we reduce with this let's say the fx component, fy getting bigger. As soon as we reduce the fx, so that means our effective force to rotate the rocker getting smaller. So, and that is the reason we say the efficiency of the transmission or efficiency of the rotation is not good. And therefore, if we have the big angle, like, if we increase this angle, you see, you can easily imagine, if we increase this angle, the vertical components of this force getting lower, and the horizontals getting bigger. So then we have good efficiency in respect of in terms of power transmission. Okay, so let's continue. When the transmission angle becomes small, so when the transmission angle becomes small, what's happened? Large forces are required to drive the rocker arm. So large forces. We have to increase the forces here to drive the rocker because of this angle, because these components of this force getting smaller. For best results, the transmission angle should be close to the 90 degrees. Of course, if it is 90 degrees, so that means the power full effective. That means the force times this length is the torque here, and we use all the force for the torque. So say close to 90 degrees as possible during the rotation. But during the rotation, since the position is changing, we cannot expect any let's say constant theta, gamma angle. This is not possible, not constant, because it is changing because of the motion of the links. Okay. This will reduce the bending. This will reduce the bending in the links and produce the most favorable force transmission conditions we explained already. The extreme values of the transmission angles occurs when the crank lies along the line of the frame. A common rule of thumb is that a 4-bar linkage should not be used when the transmission angle is outside the limiting of, let's say, 45 and 135. So those are the limiting positions. Okay. In some instance, the length of one of the links must be a specific dimensions. Most commonly, a target length of the frame is L1, is specified L1. Most commonly, a target length of the frame L1 is specified. Why L1? Because, you know, we want to locate these mechanisms somewhere. And therefore, in the machine, we have to install somewhere in the machine. And this distance here, given actually by the machine. This is the L1. So, however, only the rocker length L4 is directly specified in the procedures just outlined, since the 4-bar mechanism was designed to attain specific angular results. This is the angular result here. So these we mean here the angular result here, delta theta 4 max, angular result. The length of all the links can be appropriately scaled to achieve the desired links dimensions and maintain the design objectives. All CAD, computer-aided design systems, have the abilities to scale the constructed geometry of a figure. So by using the CAD system, computer-aided design system like the AutoCAD or Inventor or SolidWorks and so on, you can easily design it. So, design of a crank rocker mechanism. But we can calculate also the, using the analytical way, we can calculate the dimension. So the analytical methods, we talked about the graphical method here. So at the beginning we said this is the way of the graphical method. So then analytical method, we can use the analytical method. And the analytical methods can be incorporated by analyzing the triangles in figure. So B here you see. To generate expression for the link lengths 2, 3, and 4 as a function of the throw delta theta 4 max, the frame length L1, the imbalance angle beta, and the inclination of the arbitrary line theta m or line M. You see here in the design we discussed line M and arbitrary angle theta m. Okay, so here you can, so L4 can be calculated like this, L1 sinus. Since we can select L1, if you say we can select L1 because of the machine where we are going to apply, what is the minimum and maximum L1 we can select, and based on this L1 we can calculate the L4 like this, and beta is imbalance angle, you know, these geometric relations here, and then we calculate a factor K4 and like this here, and then we can calculate L3 and L2 and so on. This is the analytic way. The geometry actually. This we're using the trigonometry and the geometric relation in this figure. So we have an example, okay. Design a 4-bar mechanism, and this is homework for you. Design a 4-bar mechanism with a stroke of 80 degrees. The outward stroke must consume 0.020 second. This is for Q, for the definition of Q. And the return is 0.025 second. The target frame length is this right here, 254. So target frame length, this is the frame length here, L4, frame length. So target length of the frame length L1 is also given. So since L1 is given, so a beta you can calculate, and you can calculate L4 and K, and then L3, L4, L2, but you have to use both of them, graphical way and the analytical way. So let's make 10 minutes break, and we will start at 14:15. Okay, let's continue. Can you hear me?
Yes, we can hear you. Doctor,
Okay,
I have a
thank
question
you. Yes?
about the homework, the ninth question. I couldn't get it. I think there's something wrong.
What is wrong?
The angle given is not the angle written on the question, and I tried my best and I can't solve it. So I might need some hint or help, I guess. If,
You mean the homework I gave via the Orlearn platform?
yeah.
Okay. Can you write an email and explain that? I will turn back.
Okay, thank you.
Okay. Thank you. So let's continue. With the synthesis. So another issue we are going to discuss is mechanism to move a link between two positions. So two positions. That means two positions is given, and we have to design the mechanism in order to realize these two positions. Especially in material handling mechanism, it is common to have a link that moves from one general position to another. That means from one position to the other position. Let's say this is the first position and the other is the second position, like this. Or this is the first position and the other is this one, for example. So it could be a link. This is a link. Let's say this is like a link, and this sorry, and the link is this link here, the link, and this is the first position of the link, and this is the second position of the link. So how can we realize or design such a mechanism? When two positions of a link are specified, this class of design problems called with two-position synthesis. So this task can be accomplished by either rotating a link about a single pivot point, or by using the coupler of a 4-bar mechanism. So like this here, we have two positions. This is the position 1, AB link, and this is the A1 B1 link, and this is the A2 B2 link. So in this figure here, it illustrates 2 points A and B that reside on a common link and move from A1 B1 to the A2 B2. A single link can be designed to produce this displacement, a single link. Could a single link do that? Maybe do that, and we'll see. You see, we have also these type of problems if we design a machine, or we have this type of task if we design a machine. And the problem reduced to determine the pivot point for this link and the angle that the link must be rotated to achieve the desired displacement. So here we have an example, and you will see that now. Two position synthesis with a pivot link. So this is the position 1 here. You see the AB1B, and this is position 2, A2B2. So how can we do that? We can do the following. So we we connect A1 with A2 like this, and B1 with B2, and in the middle we draw a vertical perpendicular line perpendicular to this AB, A1, A1, A2, and same for the B1 and B2, and in the middle perpendicular line to the B1, B2, and those are intersect here the point C. And you see the link actually here, the real link. Here, this is point C, and this is the first position, and this is the second position of the link. So here's explained how we do that. Construct two lines that connect A1 and B1 and B1, B2 respectively, and construct a perpendicular bisector of A1, B1 and A1, A2, and construct a perpendicular bisector of B1, B2, and the intersection and so on. So no need to read it. So you already you have seen. It is very easy, very simple. Design. And two position synthesis of the coupler of a four-bar mechanisms. What we can say additionally, in an identical problem to the one presented in the preceding section, figure 5.9, and this is the A, illustrates 2 points, A and B, and linked and the move from A1, B1 to the A2, B2. Some applications may make a single pivoted links useful, such as we already learned. But in this case, the coupler of a four-bar linkage useful, such as when the pivot point of the single link is inaccessible. So that means, so it could be also difficult, inaccessible. So that means, let's imagine we have such an application here, and we connect A1, A2, and B1, B2, and the perpendicular here, and perpendicular there. So we have the cross point. This is okay. But if we have such a situation, then A1, A2, and B1, B2, B2. So A1, A2 is, let's use another color here. So A1, A2 here, and B1, B2, like this. So this is, it goes so in that direction, and it goes in that direction. So you see the length here, huh? Do we have such a place in the machine so that we can say, okay, we create this mechanism using only one link. It's one link. So because the members here, the A1 and B1 is rotating about the point C, let's say here, and and this is the distance from the links to the center. And if we don't have such a place in the machine, so we have to, let's say, have another solution. We have to think about another solution. So is there any other solution possible? Because we do not have so much space in the machine. So inaccessibility, this is the inaccessibility. And in this case, the coupler of a four-bar linkage, four-bar linkage can be designed to produce this required displacement. That means maybe we cannot solve this problem using only with a single link. We need a four-bar mechanism, coupler, couple crank couple crank rocker mechanism, for example. So appropriate lengths must be determined for all four links and the locations of pivot points, so that the coupler achieves the desired displacement. So this is the coupler, and we can think in that direction. So this is the say the coupler A1 and B1. So B1, sorry, B1, and let's say this is such a mechanism, four-bar mechanism. So this is the first position, and if you rotate them like this, and let's say use this second position for the other course here. So this the position here, and this is also has to turn like this to this position, and this is the second position of the link of coupler. This is the first blue one and second. So that means we can manage to solve this problem maybe in certain cases only with a single or with a link, but in some cases we cannot realize with a link, and we need a four-bar mechanism. That means crank rocker. So there is an example here showing this string. Here you see the AB is given, A1 and B1 is given here, and the second position is A2, B2 here, and you know if we can of course we can draw the we continue to draw the lines here in that directions, and here in that point we can say we have only one rotation point of the one links, and we can realize this to desired position. But if we don't have such a place in the machine, so maybe we have to think for this solution. We have to think about this solution. Here, for example, this is the D and C, and the A1, B1 turns to this position, moves to this position. So this is the angle here. For the rocker, and angle for the rocker, and this is the angle. Let's use another one. This is the angle for the crank or crank. So we create two pivot points instead of one, and we reduce this is the dimensions because of the space we have in the machine. So the design is very simple, as you see here. What we do actually, we okay. So we connect as we did in the past, say in the previous example, A1, B1, and also say A1, A2, and then B1, B2, and in the middle a perpendicular line to B1, B2, and A1, A2, the same perpendicular line. And depending on the space we have in the machine, we can select C and D. We can select the position C and D. It could be also like this here, or this. Depends the place we have. Okay, so how can we solve the problem if we have three positions? We discussed two positions. So if we have three position like this here, so then this is the first one, A1, B1, and this is the second position, E2, B2, and the third position here. So how can we solve this problem? And because we can solve these problems in that way, you see, we connect again A1, A2, and B1, B2, and also B2, B3, and A2, A3, okay. Then we use the same methodology, to design it. Draw the perpendicular line like this here, and here also, and we have here one point, and the other point is here somewhere, the pivot point here. This is the between first and second position, and this is the second and third position. So 2 points, and then at the end we have our mechanism. This is you see here the first position, A1, B1, and the second position, A2, B2, and the third position, A3, B3. Okay. So we finished this part, the synthesis of the mechanism, and now we change. We will start the next chapter. Next chapter means we will talk about the velocity. So the velocity I'd like to show you some mechanism to have a feeling about what means velocity in mechanism. Till now, we discussed actually the position, displacement, and the length of the mechanisms, length of the links, and design or analyze a mechanism and all those things. So let's say we design a mechanism, and we must know maybe the velocity for certain points or acceleration for certain points, and how can we calculate the velocity and acceleration for certain points. This is we are going to discuss. Mechanism used in so much. You see what means mechanism. Very interesting video, I guess. And you create all this motion by only using the electric motor here. You have only one electric motor, so consider it is very important. Huh? You have only one electric motor here, one rotational motion here, coming from the electric motor. And it's the electric motor here. Huh? So there is another saving machine, but you have to also mechanism used in saving machine mostly, textile machine, also other type of machine. So maybe I have go a little bit faster, stop the assembly, and now you see how does it work, huh? And there is only one motion, rotational motion here, rotary motion comes from electric motor, and you see lots of combined motion is necessary in order to use a sewing machine. And all means mechanisms. Huh? There are lots of mechanisms used inside of these machines. Linkage mechanisms. So, And therefore, you see, the speed is velocity is very important. And these service machines, they sell, and the producer said maybe it produced in 1 minute so much. Depends on the velocity, speed, and the produced the cycle time, and so on. Is very important. Therefore, speed is a critical performance factor, and we will talk about now. So what is speed? Huh? So we checked already what is speed. So then here determine how fast parts of machines are moving. Important when concerned with the timing of a mechanism. So velocity analysis involves determining how fast certain points on the links of a mechanisms are traveling. Velocity is important because the associated the movement of a point on a mechanism with time. Often the timing in a mechanism is a critical issue. So let's talk about the velocity. So generally, rigid body motion consists of linear motion and the rotary motion. You may remember from dynamic, there are 3 types of planar rigid body motion. Planar. We are talking about the planar motion, not in general motion. So why? Because the mechanism we are discussing in this lecture, slider crank mechanism or the crank rocker mechanism are the planar mechanism. So the 3 types of planar rigid body motion is here indicated. One of them is the part of rectilinear translation, rectilinear. That means like our crank rocker mechanism. Here we have rotary action. Yeah, I will show now. We have here the, let's say, the inline crank slider. Like this. So it has to rotate. And here has to make the linear motion. This is the linear motion. The part 4 here, part 4 make the linear motion. And this is the link here. This is the part 1. And this is the part 2 and the link 3. So, you know from our discussions, previous discussions, that the link 2 undergoes a circular motion, rotation, pure rotation, like this, pure rotation. And we know also this is a linear motion, linear motion. And what about the link 3? Link 3 undergoes general motion, general planar motion, like this here. So general planar motion. We have here linear motion, rectilinear, but this is the part of the curvilinear, not rectilinear, because it's not, let's say, the position is the speed is changing within the time. And here we have the rotation about a fixed axis. This is this one, rotation about a fixed axis. So here, and the link 3 undergoes general planar motion. And therefore, this is the very complex one. I need to analyze the speed or velocity, or to calculate the speed and velocity on this link is the most, let's say, the complex one. And the circular or linear motions are compared to the link 3 is relative easy. So let's go step by step. Here we have, we will discuss first the linear velocity. Linear velocity. What means linear velocity? So the magnitude, I mean, if we talk about the velocity, we don't say the speed. Speed is a scalar, scalar value. Velocity is vector. So therefore, we are talking about the velocity. That means about a vector. And if we talk about the vector, we have the magnitude and we have directions. So the magnitude here of this vector, the velocity vector, is straight line, instantaneous speed of a point, straight line. And direction is the instantaneous directions of the movement. That means for an instant, maybe it undergoes a general plane motion, linear rotation are mixed, but for instantaneous, for instant time, let's say for the time being, it undergoes a linear motion. So linear motion, we consider in that way. And you see the picture here. So these pictures show us. So there is a link. Let's have another color of this. So there's a link here, triangle here, you see, and it is, let's say, the rotating around the point A here, point A, let's say, so, and counterclockwise with the angular velocity omega, and we can actually calculate the VA and VB if we know this distance. We know from the dynamic. So if we know this distance here, and if you know the omega, I mean the angular speed, and also this distance and omega, we can easily calculate the magnitude and magnitude, and the position must be like this, perpendicular to the line. That means to the line O. Sorry, I had to change it, and this is not, couldn't be, let's say O. I have to take away, and here let's write here O. Let's say this is point O. Okay. The speed BA directions perpendicular to the point to the line AO, because this is the line connect the point A with the point O about which the point A is rotating, and the same here for the B. And magnitude wise we can say, okay, VB is equal omega times the length OA. sorry, OB. OB, this is the length OB, and the omega is this is the magnitude. Magnitude. Okay, the direction we know already. VB direction we know in that direction. And same for VA. VA is also equal, magnitude-wise, VA is equal omega times OA, this length. Okay, here we also remember from the dynamic that the calculation of the speed is a first derivation about the with respect to dt, and v is equal, dr is the position vector, dr over dt, and dr is the, say, the position, t is the time, and if a point is driving undergoing this part or curve, so here we have the displacement, that means the position is changing with the time, you see here, and therefore dr over dt defines the velocity of the point moving on this path, and we can write in that way: v is equal dr over dt, or dr is equal v times dt, and this is the small portion here, and therefore we can say this is the linear motion here in between. So the linear motion here. Small portion of the path, dr over dt. So let's have an example, and we say we have a hydraulic cylinder extend at a constant rate. Constant rate, that means the speed is constant. So speed is constant rate, to its full stroke of, this is the full stroke is 256 millimeters in 4 seconds. So determine the velocity of the rod end. So this is the, the cylinder, and this is the body, this is the piston. Rod is moving here. This is the piston rod. Let's call it piston rod. And we have to calculate the speed of piston rod. And piston rod, what is the stroke? Let's say it starts from here, the initial position, and go in that position. Is too much, but nevertheless, too much position. This is the stroke, maximum stroke, and how much? 256 millimeters. That means delta R displacement is equal to 256 millimeters. So 200 millimeters. Okay. And the time, delta t. Delta t is equal 4 seconds. 4 seconds. And the speed, since it is constant rate, speed is equal delta R over delta t, and this is equal to 156 over 4, and is equal 64 meter per second. Okay. So millimeter, sorry. Millimeter per second, because it's millimeter units. So also it's a very, very simple question, but I mean the linear motion and the linear actuator, hydraulic cylinders, and we can calculate the speed in that way. Okay, so we finish for today, and we will continue next week our lessons. So have a nice week, and you already know that exam is in the week. I don't know the exact date, but midterm exam is when it is in the week. Starts with 10th of April, and then the exams will be online as far as I know. Huh? So maybe when so what means when is the hardware? What's the hardware? I couldn't understand. Homework. Homework. Okay. So homework. I have given the date, and you have to finish till I don't know 7th or 6th of I don't know. You have to finish, and you have to scan and send to me via email. Okay. The homework. Okay. So if not, okay, if not, maybe before, let's say before the midterm, huh? Before the midterm, you have to send it. Before, let's say before the end of April, huh? Okay, have a nice week. Bye-bye.